back to Know What's Cooking, where we're changing the world one recipe at a time with a splash of physics. And if you've been following the series, you see that often those recipes are cooked on an induction cooktop. So I thought I'd spend a little time talking about the physics of induction cooktops. Electricity is simply the flow of electrons in a wire. Now there's two types of electric current. One is direct current, which happens when we plug something into a battery, which just means the electricity continues to go around the loop in one direction. Or there's alternating current, which happens when you plug something into the wall, which is connected to the electric grid. And alternating current simply means that the electrons are still moving, but they move back and forth. In fact, 60 times per second in the United States. All right, so next we have to understand two important connections between electricity and magnetism. The first of which is that when electrons are traveling in a wire, there is automatically a magnetic field around that wire, and we can show that with an electromagnet. Take a piece of wire and wrap it around a screw. This is an electromagnet, but we can see when it's like this, it is not a magnet. It's not able to pick up these paper clips. However, when we attach it to a battery, we see as soon as we have electrons flowing in that wire, we do in fact produce a magnet. As soon as the electricity is disconnected and the electrons stop moving, we also no longer have a magnet. Another important point about an electromagnet is that the polarity, or where the North Pole faces, depends on the direction of the electrons. So if the electrons are flowing through the circuit one way, the North Pole will be up. And if the electrons are flowing through the circuit a different way, the North Pole will be down. That's important. Okay, now for the second connection between electricity and magnetism. And that's just to ask the opposite question. If the electromagnet showed us that moving electrons creates a magnetic field, is it possible that a magnetic field can induce the flow of electrons? So here I have a very strong magnet and also a coil of wire. This is just a wire that goes around and around and around, and the two leads come out and connect to this beeper. This beeper will sound when the electricity moves in one direction. So I'm going to put this coil of wire in this large magnetic field, and I don't hear anything from the beeper. However, if I move this wire relative to the magnet, therefore allowing the wire to see a changing magnetic field, you see that I do induce the flow of electrons in this wire. That's amazing. All right, now let's put this all together to explain an induction cooktop. First of all, inside this induction cooktop, there's no heating element. It's just a large electromagnet, which by the way, is plugged into alternating current electricity. Therefore, the polarity of the magnet is changing. Rather than this changing magnetic field inducing the flow of electrons in this coil of wire, it is now going to induce the flow of electrons in a cast iron skillet. And just the same way that electrons moving through a coil resistor heat up the burner, the electrons that are moving in this cast iron skillet will heat up the skillet. You go directly from this changing magnetic field to the movement of electrons in your pan. And this is what makes induction cooktops so responsive. As soon as you change the strength of the electromagnet, you immediately change the electron movement in the pan, which immediately changes the temperature of the pan. This makes it very energy efficient. I definitely think you should give it a try. This was clearly more than a splash of physics, but hopefully it was helpful. Thanks.